Okay, I promised we would combine these, or maybe I threatened that we would combine these. And when we do, Gibbs free energy is the result. We also refer to this as chemical potential. So it's like a potential energy, but related to the chemicals that are in here. Um, Gibbs free energy, it's the total energy in a system that accounts for the enthalpy and the entropy. So, this is the measure that we will use to determine favorability or spontaneity, and it has a combination of delta H and delta S. So, the equation that you will need, delta G equals delta H minus T delta S. This is on the equation sheet, but you will probably have it memorized because we are going to do a bunch of scenarios with it, and it will it will come back continuously throughout this unit. So when we do this measure, if delta G is negative, this is what we would call thermodynamically favorable. If delta G is positive, this is what we would call not favorable or non-spontaneous. So temperature is something that goes in here without a delta. And the temperature can have a drastic effect on the favorability of a system. So what we're going to do in looking at these scenarios and in general, one thing we're going to do is assume that delta H and delta S don't change as the temperature changes. Now, officially, they change as the temperature changes. However, they stay mostly constant over such a large temperature range that we can use it. So when we need delta H or delta S values out of the appendix, the stuff in the appendix is only technically good for 25 degrees. We will be able to use those values even when we're not at 25 degrees. What we're going to look at in these next four scenarios is the balance of delta H against minus T delta S. So you can see, right, delta H, the direction we want it to go to support favorability is we want it to be negative. But delta S, to support favorability, we want it to be positive. We're subtracting T delta S, so we can kind of make that negative. But in the end, the thing that will determine if delta G is positive or negative is how those two terms are balanced against each other. So let's look at some examples and what that means for the spontaneity or favorability of a reaction. So if delta H is negative and delta S is positive, both factors favor spontaneity. This reaction would be favorable or spontaneous at all temperatures. So what this means is my delta H is negative. My entire T delta S term, delta S is positive multiplied by a negative, so I have a negative value. If I add two negative numbers together, I get a negative number. So I could change the temperature as much as I want. It could go higher, it could go lower, and my delta G will always be negative. So the reaction will always be favorable. Second scenario, delta H is positive, delta S is negative. Both of these support non-spontaneity or not being favorable. This reaction will be unfavorable at all temperatures. So non-spontaneous at all temperatures because my delta H is positive. My delta S is negative, which makes negative T delta S positive. And when I add two positive numbers together, there is no way to get anything other than a positive number. The next two scenarios will depend on temperature. So if my delta H is positive and my delta S is positive, it depends on what the temperature is, on whether or not this is a spontaneous or favorable reaction. So delta H positive, if delta S is positive, then negative T delta S is negative. So I have a positive term and a negative term. When I add these together, getting a positive value or a negative value as the result depends on the relative magnitude. If the positive term is bigger, the result is positive. If the negative term is bigger, the result is negative. So, in order to be spontaneous, the negative T delta S must be bigger, and I can make that term bigger by increasing the temperature. So, this reaction, a reaction that has this set of conditions, I guess conditions is the wrong word, this set of thermodynamic characteristics, the reaction will be favorable or spontaneous when the temperature is high enough for the minus T delta S term to overcome delta H. Last scenario, also temperature dependent when delta H is negative and delta S is negative. So delta H is negative, exothermic. If delta S is negative, then negative T delta S is positive. So again, I'm adding a negative and a positive number. My result will depend on their relative magnitudes. So my reaction will be favorable or spontaneous when the temperature is low enough for the delta H term to be the dominant term in the addition. So low temperature will keep that minus T delta S term small, and the amount, essentially the amount of increase in entropy in the surroundings helps make up for the fact that our reaction is getting more ordered. For these last two scenarios, you can calculate the temperature at which the reaction changes over. So at what temperature do I need to get to flip this into being spontaneous? Or what temperature do I have to stay below to make sure that this stays spontaneous? There is a derivation of this if you ever want to see it. It's all just hinging around delta G being equal to 0, right? Because we're defining our spontaneity or favorability around delta G being positive or negative. So that's the flipping point. I will just give it to you. This is the crossover temperature. And you can find the crossover temperature if you do delta H divided by delta S. So delta H in energy units, delta S in energy per temperature units. So the result of this will be a value in Kelvin. Just don't forget to watch your units because, like I said, delta H is usually in kilojoules because it's pretty big. Delta S is usually in joules per Kelvin.